In the last lecture, I talked about how crystallization and melting can be deduced from understanding of ternary phase diagrams. Now, in this class, in this lecture, I will talk to you about how crystallization and melting occurs in a ternary system again, but this time, out of the three components, two components form a solid solution. So two components form a solid solution. If that happens, then you have a problem which is very different from the earlier phase diagram. Is that in the earlier phase diagram, all the crystallizing phases were pure. In this, the crystallizing phases, one of them is pure and the other one is a solid solution. So, there is now a difference, a major difference. In the first ternary diagram, the ones in the last two lectures, you did not need to find out the composition of A, B and C minerals because they were pure. Here, you have to not only find out, in the last lectures, you didn't have to find out the compositions of the mineral phases because they were pure. In this, you have to find out the composition, not only the solid which actually is formed by a pure phase and the other one with another phase, but that phase composition is not constant, it's not pure. There is a variation. Now this introduces several complexities, and understanding such diagrams is a little more complex. So I will again start as always with the basics, and then we will go over into the ternary system. Now the basic reaction between plagioclase liquid and plagioclase melt. So essentially it can be written in terms of albite in solid is equal to albite in melt. That's the equilibrium. And anorthite in solid is equal to anorthite in melt. If you combine the two, you have plagioclase in solid equal to plagioclase in melt. So essentially, when you are discussing equilibrium between plagioclase and melt, you're essentially discussing albite in solid equal to albite in melt, a reaction. This involves any exchange between the solid and the melt, and anorthite in melt, which is essentially exchange of Ca and Al in melt and in the solid. That's the important point here. If you understand this, then we go over to the next point. Therefore, we can write, if you have got the point that the equilibrium plagioclase in solid, plagioclase in melt, you can treat it with either of the two phases, because XCA of albite plus XCA of anorthite is equal to 1. So you can deal with it with any one equilibrium. Let's take one of them. So NaAlSi3O8 in melt is equal to NaAlSi3O8 in solid. That's it. This equal to sign is essentially equilibrium, and these two are stoichiometrically balanced. If you do this, then this equation, delta GR of the reaction at a particular pressure temperature, it is, I'm now ignoring this because you know what it means, can be written as delta R 0, okay, pressure temperature, minus T del SR 0, pressure temperature, plus P delta VR 0, pressure temperature, plus RTLN activity of albite in plagioclase divided by activity of albite in melt. That's the expression. And this, because del GRPT is equal to, at equilibrium is equal to 0, this is the basic equation. Now, like I have always tried to avoid activity, because activity involves activity coefficient, which can be a complex term. We have talked about this before. It's, if you want to see the equation better, see through the equation better, let's say we replace it, assume it to be an ideal solution. This is an assumption that it's an ideal solution. So, assuming ideal solution, approximation, we can write 0 is equal to delta HR minus T into delta SR plus P into delta VR plus RTLN X albite in plagioclase divided by X albite in the melt. Assuming solid solution, that means activity of albite in plagioclase is also ideal, and activity of AB in melt is also ideal. Both are incorrect assumptions. Both are imprecise assumptions. But it is easier to see that. Now you can see, if I can write it, then X albite in plagioclase divided by X albite in the melt would be equal to exponential minus 1 by RT into del H0 minus T del S R0 plus P into delta VR0. This is your expression. This is your expression. So now, if we take this one, I will try to change the pen, it's not nice. This one here, and this one. If we take these three as thermodynamically known values, then this expression means X albite in the plagioclase divided by X albite in the melt is therefore a function of pressure and temperature only. Function of pressure and temperature. Do you see this? If I don't assume that these we know and we know, and then this ratio, which is essentially a ratio of the compositions, assuming ideal solutions, is only a function of pressure and temperature. And another important thing, normally when we are examining ternary systems, we try to take it isobaric section. So normally it becomes a function of temperature. Therefore, X albite in plagioclase is equal to X albite in the melt into a function of temperature. So now you see there is something interesting coming up. The composition of the plagioclase, X albite in plagioclase means anode height is 1 minus X albite. So the composition of the plagioclase is a function of the composition of the melt as well as the temperature. Remember this, as well as the temperature. And from this ratio is a function of temperature. That is why in the phase diagram that we do, so we write albite, anode height, and this is the temperature axis. This is the melting temperature of albite. This I derived before, and this is the melting temperature of anode height. This is how the phase diagram looks like. This is liquid, this is plagioclase solid, and this is plagioclase solid plus liquidity. This is the ratio of X albite to X. What do you mean by the ratio? If I say, for example, if I draw a line, that means this is a particular temperature T, say at a particular temperature T, then this is X albite in the melt, and this is the X albite in the solid. Do you see that? This is the liquid us, so this is the composition of the melt, X albite in the melt, and this is in equilibrium with X albite in the solid, and this is temperature. Now you can see one very interesting thing that happens. The composition of the plagioclase, relative to the composition of the melt is shifted to the high temperature side of the phase diagram. That means, if in a diagram where you have albite and anode height, if you plot X albite melt, then X anode height melt has to be plotting on this side of the diagram. If this is X albite in the melt, X anode height will plot to the right side of the diagram with a higher melting temperature. You see that? This is very, very crucial when we work with the ternary diagram. Remember this, that X albite of this plagioclase should be anode height richer compared to that in the melt. Have you understood? Sorry. In this is anode height 1, so X albite here is equal to 0, here X albite is equal to 1. So here you remember that the plagioclase composition of the solid plagioclase composition will have a composition which will be richer in anode height content than the melt. Remember this. So there are a few things to remember from this derivation. That the ratio of these two is essentially a function of pressure and temperature. If we ignore the pressure effect, this is a function of temperature, the ratio. Also, the composition of the plagioclase will be a function of the composition of the melt and the temperature. Composition of the melt and the temperature. And the second point that you should remember, that the crystallizing plagioclase, the solid, will be anode height richer compared to the melt composition. This is very, very important, and you will see the tremendous effect of this when we work with the ternary phase diagram. But this should be known right at the beginning. I will stop the class a bit. I will start again just a moment. Okay. So we come back to this ternary diagram, and this diagram looks like this if we draw it in 3 dimensions. Let me try and draw. You know my drawing is very famous. So that's not too bad. So that's albite, anode height, temperature of melting of albite, temperature of melting of anode height. This is, say, diopside, temperature of melting of diopside. And this point here is eutectic, temperature of eutectic of albite diopside, and this is temperature of eutectic anorthite dioxide. So this diagram is essentially a three-dimensional representation of the diopside albite anorthite phase diagram. And then the isotherms, as you know, would be like that. This is how the isotherms would look like. This surface is the plagioclase liquidus surface. This surface would be the plagioclase liquidus surface. And this will be the surface for diopside. So you have two phase fields, the diopside phase field and the plagioclase phase field. And the two intersect along a line which connects the eutectics between anorthite diopside and albite diopside, and this is the direction of the eutectic, and the melting temperature decreases in this way. This boundary curve slopes this way. So if we now project these points onto this diagram, and this point onto this diagram, and then I join this line and I make this red. So this is what I will see when I project the whole thing on the compositional plane diopside, albite, anorthite. This is what I will see. Diopside, albite, anorthite, something like that. Temperature of eutectic, anorthite diopside, temperature of eutectic, albite diopside. This is diopside phase field, and this is plagioclase phase field. And this is 50, 25, 75, 50, 25, 75, 50, 75, 25, and that's how the calibration goes. The isotherms would look like this. This is how the isotherms would look like it. The temperatures of the isotherms increase this way, and the temperatures of isotherms increase this way. This is how the composition is shown. I am sure that you must have understood this diagram. It has been taught to you. But now we come to a very interesting position. Look at this field, albite and octite. This is the vertical field. Remember, it's a projection of this. Now, I told you, I am drawing this with a blue line. Say, for example, if you take an isotherm passing through it, this will be the composition of the solid, and this will be the composition of the liquid. Have you understood? So at the base, say this is anode height 75, this point. So now, where will be the composition of anode height 75 if it was the solid? This is anode height 75 of the liquid. Where will be anode height 75 of the solid? Remember, when I talked about last time, it should plot on this side. So this will be anode height 75 in plagioclase. Do you understand? Somewhere here. It should be right of anode height 75 in the liquid. Anode height 75 of plagioclase should be shifted to this direction. Have you understood? Similarly, if you take this as anode height 25, this is the anode height 25 of the liquid. The solid anode height 25 will be here. It will be to the right of it. So in this diagram, the one on the black line represents the composition of the plagioclase, albite and anodite component of the plagioclase in the blue. But there will be another set of points, the composition of albite and anodite in the melt, albite and anodite components in the melt will be given by these black lines. There will also be another set of lines in blue which will give you the composition of the plagioclase that is in equilibrium. So anodite 75 of plagioclase will not coincide with anodite 75 of the liquid. No, never. It will be on the right hand side. So all will be right hand side. It will be same only when you have anodite pure and albite pure. Both will plot at the same point. Because then is no more a solid solution. These are pure phases. Other than that, the plagioclase solid solutions, the composition of the plagioclase as given in blue, should for the corresponding 75 anodite here, it should be shifted to the right. If there is for the melt anodite 25, the anodite 25 of the crystallizing plagioclase will be shifted to the right. They will not plot at the same point. This is what I meant earlier. So, in this diagram, there will be two graduations. One in black, which will give you the proportion of albite and anodite in the melt, and one in blue, which will give you the proportion of albite is to anodite in the crystal. When you look up any book, either you can look up by the book by Winter, or you can look up in the book by Phil Potts and Ague, or any standard petrological books. There will be two sets of lines. I will tell you what are those lines. Now say, this binary, if you say this is the binary, this is, this surface. This is only where plagioclase is. There is dioxide is 0 along this line. Dioxide is 0. But what happens if dioxide is added? Say, for example, you have added some amount of dioxide and then your composition should lie here. Then what will you do? What will you do? Here, this is the composition of the melt is very easy to find out. Very easy to find out on this line. But what will be the composition of the solid plagioclase? Have you understood? So this is done using experimental calibration. So experimentally, theoretically also it is done, but because the polymeric models for silicate melts is not very well known, so there are uncertainties. But there are a lot of experiments have been done to find out how, now these are called isotherms. These blue lines, these compositional lines are called isoplets. Isoplet, P-L-E-T-H. So there will be all isoplets between anode height 100 to anode height 100 to anode height 0 isoplets should also form here. So the diagram, when I plot the isoplets, now this is this is the heart of the problem. You should be very careful. If you have any questions, you please let it know through the melt. But I think after I tell you, it won't be, you can refer to the books by Winter, as I told you, or book by Phil Potts or Ague. Both of them, there the same thing is discussed, but not in so great detail that I am telling you, but you must consult those two books. So what will happen here, in the final diagram, you will have this dioxide, albite, anode height. This is the boundary curve. Temperature of eutectic, dioxide, anode height. Temperature of eutectic, dioxide, albite. And you will have the isotherms plotted like this. It will be shown in the diagram. And this is 50, 75, 25, and so on and so forth. This is anode height. Also, you will see in this diagram, there is another set of lines. Lines like this. This is called the isoplet. And this one here is called the isotherm. Have you understood? Now, what is this isoplet? Look, say for example, I will just draw it, you can read it more details in the book. Say I say this is AN75 isoplet. Means what? AN75 isoplet. Means what? Along this line, remember, I derived this equation just before. X albite in the melt, X albite in plagioclase is equal to X albite in the melt into a function of temperature. Did I write this before? Yeah. So, X albite in plagioclase, or it doesn't matter. 1 minus X albite is a no thought. It doesn't matter. The composition of the plagioclase is a function of the composition of the melt and temperature. So you see, these are the temperatures, right? These are the isotherms in the black. And along this line, which is in red and labeled anode height 75, what is changing? Two things are changing along this line. What is anode? First of all, what is anode height 75? Anode height 75 is the composition of the crystallizing plagioclase. That's the first thing you should know. Anode height 75, when I write, this is an isoplate. What is this isoplate? Along this isoplate, plagioclase of the composition of anode height 75 will crystallize. Have you understood? Now, at this point, this is the temperature. At this point, this is the temperature, this is the temperature, and this is the temperature. So, this composition joins all lines in this, and if this is the point, this is the composition of the melt. Can you see? This is the composition of the melt. So much is albite and so much is anode height. And that will not be 75. That will be less than 75. Anode height 75. It will be less than anode height 75. So what is happening? Along, if you take a point here, then you not only get the temperature from the isotherm, but you also get the composition of the crystallizing plagioclase. The composition of the crystallizing plagioclase. Is this clear? Once again, I will repeat because this is very crucial to understand. Remember this diagram. The composition of the plagioclase is a function of the melt and a function of the temperature. Right? These lines, these red lines, essentially represents lines along which the composition of the crystallizing plagioclase is constant. Have you understood? In this case, it's anode height 75. If you go here, it's anode height 60. If you go here, it's anode height 40, and so on and so forth. So essentially what we are dealing with here is this part of the phase diagram where is plagioclase liquid as surface. This is the composition which is in equilibrium with anode height 75. Have you understood? So this anode height 75 composition may not be here, but it will join with the anode height 75 composition marked in blue. This is not anode height 75. Anode height 75 is somewhere else. This tells you that if you crystallize the melt at this point, then this is the temperature of crystallization and anode height 75 will crystallize. But that does not mean that the point is here. It does not mean that. Have you understood? This is very, very crucial. Now let me just start one of this. It's not very easy to understand this phase diagram, but I think we should make a start somewhere and maybe we will try and get into it more. Remember one thing, those red lines that I did are the lines along which anode height 75 plagioclase will crystallize. Have you understood? And when the line touches the base, that composition is not anode height 75. No, it's not. But there will be a point where it's anode height 75. That is the point where it will be anode height 75. If possible, I will send you a PDF of the diagram with both the isotherms and this. I will try to figure out from somewhere. So, let's start our phase diagram. Study the phase diagram basically. Now, I will just start it. We will continue with this diagram later on. Dioxide, albite, anode height, boundary curve. Let's say we take a melt composition here. Once again, these are the isotherms. And these are the isoplets. These are the isoplets, so it forms some sort of a net. Now let's say we take this point, say we start crystallizing. Let's say we have this point L0. Now what is L0? This is a melt, L0. Now I draw a horizontal line. I draw a horizontal line, L0. So this is the proportion of dioxide. So let's say if we draw here 50, 75, 25. So this may be roughly about, let's say 60. So this is dioxide 60. Dioxide is 60. What remains is plagioclase, because that's the only other thing. So plagioclase is 40. The total is made up to 100. But plagioclase 40 has also to be divided between albite and anorthite. Is it not? Plagioclase is not a pure phase here. Albite and anorthite. So what do? We can take a line and join it here. You see, it's a similar triangle. So this is 50, this is 75, and this is 25. So you can see, if this is the case, then you have a case where albite, anorthite in the melt is roughly, say, 40, and albite is roughly 60. So your L0 essentially is dioxide 60, albite 60 into what is remaining, 40. That means albite is 24. 0.6 into 40. Have you understood? 60.6 into 40. That's 24. And what is anorthite? 40.4 into 4. That is 40, 60. So that is 60. This is your answer. Dioxide, albite 24, anorthite 16. Why did I not write plagioclase? Because when I start crystallization at L0, there is no plagioclase crystallizing. Unless it touches, unless the melt has the temperature, then you call plagioclase. But when I write this for melt, it is wrong. It is wrong because there is no plagioclase. There is no plagioclase. There is only albite and anorthite. Dioxide, albite, and anorthite as far as the melt is concerned. So the melt composition properly written is L0 is dioxide 60, albite 24, anorthite 60. These two add up to 40. This is what I wrote as plagioclase 40, but that is incorrect. Why? The melt has not crystallized anything. You can say, but you have written dioxide. The melt does not have dioxide, also does not crystallize. I said, yes, correct. But dioxide is a component. Dioxide is a component in the melt. So I have no option. So dioxide, I have no option. Because if it crystallizes, it's also dioxide. If it's in the fluid, if it's in the melt, it's also dioxide. So with dioxide, I have no problem. But I can't write plagioclase 40 because in the melt, there is no plagioclase 40. Plagioclase 40 is only when plagioclase liquidus is reached. Then you crystallize plagioclase, not before that. Have you understood? Okay. Now, so we start with the liquid L0, which has dioxide component 60, albite component 24, anorthite component 16. Is that all right? So it is like this. Now, what happens when the milk touches the liquidus of dioxide? Dioxide will crystallize. The moment the milk touches the liquidus surface of dioxide, dioxide will start to crystallize. Right? So the moment dioxide starts to crystallize, the milk composition has to move away from dioxide. Yes or no? Away from dioxide. So the only way this can be done is you have a line and you join it. Let's say this is L1 and this is S1. What is S1? S1 is dioxide 100. The solid S1 contains only dioxide. Only dioxide. Dioxide 100, and dioxide is a pure phase. CaMgSi2O6. That's the composition of dioxide. So dioxide starts to crystallize. You can ask me, sir, how did you plot L1? I understand, okay, dioxide will plot here, so this is S1. Fine, dioxide will precipitate. How did you do L1? I did not do it. I only plotted this. You have to say, again, let's say this is M and this is N. This one is N and this one is N. So, M divided by M plus N, this value is the melt fraction, yes or no? Is the melt fraction. M divided by M plus N is the melt fraction. Now you tell me how much crystallization has occurred. 10%? Fine. Then I write M divided by M plus N is equal to 0.1. That means 10% crystallization. So this M divided by M plus N should be equal to 0.9 because 10% crystallization has occurred. So 90% is melt. So now M is equal to 0.9 N plus 0.9 N. I have done this before. It's the same thing. I have not changed anything. So now you have, if I subtract this, 0.1 M is equal to 0.9 N. So N will be equal to 0.1 divided by 0.9 into M. Have you understood? So, you see this is M. This value will not change. This is the fraction M divided, but this value will not change. So, if you know this length from your graph sheet, triangular graph sheet, and I ask you, what will be the composition of milk at 10% crystallization? What you have to do? 10% crystallization means melt fraction 0.9. If you do that, then N, this term, this length N, will be equal to 0.1 divided by 0.9 into N. Have you understood? So now, if you have a measure of M, you can multiply to find out the length from N. So you can find out this L1 is the position if it is 10% crystallization. Have you understood? If it is 10% crystallization, then okay, this should be the point L1. If you say, no, 20% crystallization, fine. So, M divided by M plus N is equal to 0.8, 20% crystallization or solidification. You go over the back calculation and you will turn up with a relationship between N and M. Remember, this has not changed. Your M value has not changed. So in a triangular graph sheet, you can measure it with a scale. Once you measure it with a scale, you can multiply the value and can get the value of L2 where this is still S2. So S2 is still diopside 100. Sorry, S2 is still diopside 100, but now your melt composition has changed to L2. So what will be L2? So you will see it is 50% dioxide now, 50% dioxide, and you can see if this is this case, we have not separated plagioclase, so that composition will remain the same. So what will be L2? L2 will be diopside 50. Diopside 50, you see we have not changed any albite and anorthite ratio, so that ratio will remain the same. We are moving on the same straight line, so we are moving on the same straight line, so that ratio will not change. So what you will have, the rest plagioclase here is 50 for the liquid. What does this mean? So L2 is equal to diopside 50 and then 50 into 0.6. So albite will be 30. Albite will be 30 and anorthite will be 20. You see, 30 is to 20, 60 is to 40, it's the same ratio. That ratio does not change. That ratio will not change. So that is very important to find out. I will wind up for today. We will continue with discussion. It will take some time. So that is how crystallization proceeds. But before you read the next lecture, I think you should go back to the book and find out if there is any problem. The most important thing is the isopleth. Remember, the isopleth gives you the composition of the crystallizing solid, crystallizing plagioclase. Have you understood? It's a locus of all locus where the plagioclase composition is fixed. The problem comes here. You will think this is anorthite 75. No, anorthite 75 will plot as where it will be on albite anorthite binary, because your line will live to the left of it. Have you understood? This is the most important thing. And the next lecture, that will become very important. So I guess I will stop here now. We will continue this in the next video lecture.